If you've watched the other episodes in this 9.5 series, you've heard me say that one-way light speeds are not equal in a moving reference frame. I showed in episode 9.5b that the difference in one-way light speeds can be detected with a Sagnac or with a Fizeau or with a Wang apparatus. But these experiments involve loops and reflections, which causes some people to question their relevance to special relativity. I think these objections will eventually be overcome, but as of the date of this video, that is yet to be accomplished. Now, I've said many times that placing clocks at either end of a linear light path is problematic, because the clocks at either end must be synchronized, and this is typically done with an electromagnetic signal. And if the speed of an electromagnetic signal is affected by the speed of its reference frame passing through a universal preferred frame, this will bias the readings on the clocks and mask the difference in light speed. So we can't use clocks at distances. Physicists have therefore tried to demonstrate light speed anisotropy with a linear interferometer. That is, one that sends light over a one-way path. One type of linear interferometer is called a Mach-Zehnder interferometer. A single collimated light beam is divided with a beam splitter. It then travels over two identical parallel paths. The two light signals are then rejoined by a second beam splitter, and a fringe interference pattern is displayed. Now, we've talked about beam splitters and interference patterns in episodes 9.5a and b, so if you're not familiar with them, please take some time to review those episodes. The difference between a Mach-Zehnder interferometer and a Michelson interferometer, the type that's used in the famous Michelson-Morley experiment, is that the light signals in a Mach-Zehnder interferometer do not make a round trip through space. You've heard me explain in episode 9.5a why round-trip light speed will always come out to speed c. So if we have any hope of demonstrating light speed anisotropy on the Earth, we need to use one-way paths. But a simple Mach-Zehnder interferometer is not going to produce a fringe shift because the two light paths are identical in both the frame of the Earth and in the frame of space. But what if we place a refractive substance in one of the two light paths? Will that make a difference? Let's demonstrate this in our animations. As we know, light will travel along two light paths at different speeds due to the refractive medium. And we showed in episode 9.5a that light speed c' star in the moving reference frame, which here is the frame of the Earth, will be equal to c divided by the refractive index n plus or minus v, the speed of the Earth through space, divided by c. Now, due to the Earth's 24-hour rotation, we might expect to see a reversal in the speed of a light path through space every 12 hours. In other words, if the dual light paths of a Mach-Zehnder interferometer point toward a certain constellation in the morning, they might point away from that same constellation in the evening. And so if the speed of the Earth through space has an influence over the speed of light traveling on the Earth's surface, we might expect some changes in the interference pattern. Or not. In order to know, we need to do some basic math. And as we showed in episodes 9.5a and b, the frame S' time required for light to travel a distance dx' in a moving frame, in other words, a fixed distance on the Earth, can be computed with the following formula: dx' over c times the quantity n plus or minus v over c. Next, we can get a fringe shift if the travel times are different for the different light paths. Well, we know that n is different for the two light paths because we have placed a refractive medium in one of the paths. So there will be a travel time difference of dx' over c times n minus 1. If we multiply this times light frequency, we get the fringe shift, frequency times dx' over c times n minus 1. This will be a very large fringe shift if n is significantly larger than 1. But it will not tell us much about light speed on the Earth unless this fringe shift changes over a 24-hour cycle. So what is the fringe shift 12 hours later? Well, we can compute this by replacing v, the speed of the Earth through space, with negative v, and we get the same answer: frequency times dx' over c times n minus 1. Unfortunately, the speed of the Earth moving through space makes no difference to the fringe shift. And so a Mach-Zehnder interferometer will not be able to detect light speed differences, even if they're real. And so once again, a novel experimental setup fails to demonstrate light speed anisotropy. Now, I don't want you going away thinking that this proves that light speed is constant on the Earth. It does not. It merely shows that, once again, the experimental design is insufficient to reveal light speed differences. So what can we do? Well, we at Ask Us Whatever have an idea. It may or may not work, and we'll certainly let you know when we begin to collect data. But I'd like to settle this debate once and for all, and I think there is a way to do it. And hopefully, that will be the topic of a future episode. Okay, that's it for now. If you have any questions, please write them in the comments sections. And if I've caused you to think outside the box, please rate this video favorably. I'm Joe Sorge, and thanks for watching.